Now we are going to talk about transformation of random variable. So first question is that what do we mean by the transformation of random variable? So let us think of a function g which is a function from R to R. Okay, so g is a function from R to R and g is a function from R to R, and suppose I have a random variable x and x is a random variable. What will happen to g of x? Is it a random variable? The question is these a random variable? And the answer to this is yes. First, we need to understand what do we mean by g of x. Note that by x we mean that it is a random variable, that means a function from sample space to real line. Okay, x is a function from sample space to real line. So by g of x, I basically mean that it is nothing but composition of g and x, composition of two functions g of x. So basically, if that x was a function from S to R, sample space to R, I have a g which is a function from R to R. So the scenario is something like that. I have a sample space here which is S, I have R here, and I have R here. So this X actually maps the points in sample space on R. Then this G again maps the sample space from R to R. Okay. So clearly, if I think about the composition G of, so when I talk about the composition of G of X of omega, then this omega is through X is mapped to this R, and then the element in R is mapped to again in R using this G. So clearly this belongs to R. Also, that basically means that G composition X, or which we are going to write as G of X, is basically a map, basically a function from S to R, and that's why basically this quantity is a random variable. Okay, so this quantity is a function which takes the element in S to R, which takes the element from S to R, which is basically G of X, and so that's why G of X is basically a random variable. Now, if G of X is a random variable, let us take Y equals to G of X. Now, natural question is that what is the distribution of Y, which is G of X? Obviously, when I am talking about what is the distribution of G of X, that basically means that we know, so our aim here is to find distribution of G of X given the distribution of X. Okay, so our aim will be to find the distribution of G of X, which is basically Y, random variable Y. Try to find out the distribution of Y given the distribution of X. What do we mean by the distribution? By distribution, I mean to say either CDF. So we will try to find out what is the CDF of Y, or we try to find out what is the PMF of Y if Y is discrete, or we will try to find out what is the PDF of Y if Y is continuous. Okay, so given the cumulative distribution function or PMF or PDF of X, we will try to find out the distribution function or PMF or PDF of Y, and this PMF and PDF obviously we will understand that whatever applicable, that will only we will able to find out. The other one obviously we cannot. Okay, so aim in this section I hope is clear to everybody. So transformation in there of random variable, we are basically have a function G, and then we try to find out what is the distribution of Y given the distribution of X. Okay, and for that we are going to discuss mainly three techniques: technique 1, technique 2, technique 3, and obviously in between there are some other concepts coming. We will see one by one. So let us start about technique 1, and technique 1 is basically nothing but we will try to find out the CDF of y given the distribution function of x. And we will try to find out the CDF of y directly using the definition of the CDF. Okay, so we know the CDF of the random variable y at the point small y is nothing but the probability that y is less than equals to small y. And because capital Y is g of capital X, so I can replace this g y by g of capital X, and then we try to find out what is the probability that g of capital X is less than y from the distribution of x. Let us take some example. Let us try to understand how this go on. So suppose x is a discrete random variable and the PMF of x is given by this function. Okay. Notice the support in this case. Support is -2, -1, 0, 1, 2 and 3. Okay. So now suppose the g function is x square. So I have the scenario of this form that I have this one that, so this is example. This is example 2.29, and we have f of x equals to 1 by 7 if x equals to -2, -1, 0, 1, and it is 3 by 14 if x equals to 2 or 3, it is 0 otherwise. Okay. So now in this case, what we have taken g of x to be x square, so that y equals to g of capital X, which is x square. Okay, so a point in the sample space goes to R using which is omega f, and then omega x square is basically omega y. Okay, so that basically means that omega value of the function y at the point omega is nothing but x of omega, that whole square. Okay, now if we try to find out what is the distribution function of y, and if we try to use the definition directly, so the distribution function of y is basically nothing but if y at the point y is, by definition, it is y is less than equals to y, which is basically nothing but probability that x square is less than equals to small y. And we know that x square less than equals to small y, that basically mean that okay, this one will be I should write in this manner, this one will be 0 if y is negative, because x square cannot have a negative value, because x can take values in the real line. Whenever you take the square, it will turn out to be positive one, and it will take value probability that minus root y is less than equals to x is less than equals to root y if y is greater than equals to 0. Yeah. So the distribution function of y can be written in these two forms. When y is less than 0, it is 0, but when y is greater than 0, I can write the distribution function of y as a probability statement over the random variable x. Now, this kind of probability I can find out very easily, because I know the PMF of x, and for different values of y, I can find out this probability. How? Let us consider several cases. First note that the y, or I write in this manner. See, the support of x is basically nothing but -2, 1, 1, 2 and 3. So clearly the values for y will be nothing but 0 square 0, 1 and -1 square 1, 2 and -2 square 4, and 3 square 9. So intuitively it makes sense that the values of y will be 0, 1, 4 and 9. So based on that, we are going to compute the distribution function of y for different values of y. So if 0 is less than equals to y is less than 1, then the distribution function of y, which is equals to probability that minus root y is less than x, less than equals to x, less than equals to plus root y. And you see that in this case, when y lies between 0 to 1, root y also lies between 0 to 1. So that means that minus root y lies between minus 1 to, so I have 0 here, so I have minus root y somewhere between minus 1 to 0, and plus root y lies between somewhere between 0 to 1. So, and when I try to find out the probability that x lies between these two values, only possibility, only where x has positive probability is at the point 0. So this probability is nothing but probability x equals to 0, and this probability is from the PMF is nothing but 1 by 7. Okay, so this probability is 1 by 7. Now let us consider next step, which is 1 less than equals to y less than 4. Because this value of y is 4, that's why I break it in this manner. And in this case, f of y, in this case, f of y at the point 1 is equals to, again, this probability that minus y is less than equals to x is less than equals to plus root y. And now notice that in this particular case, plus 1, my 4 is here. So minus, when y lies between 1 to 2, minus root y lies between somewhere minus 4 to minus 1, and plus root y lies between somewhere between 1 to 4. And so that means x lies between minus root y to plus root y. Actually, take all the values of x equals to 0, 1 and minus 1. So that basically means that probability that x equals to 0 or x equals to 1 or x equals to minus 1, and this probability again I can compute from the probability density function, and at the point 0, 1 and minus 2, the probability density function is 1 by 7. So that probability, the required probability is 3 by 7, and we have that this quantity is 3 by 7. Similarly, I can now, I will go for the step, I will go for 4 is less than equals to y is less than 9, and then the next thing we will need to check what will happen if y is greater than or equals to 9. And I am not going into writing all those things because these things are quite simple, and you can see that in this case the similar way you can calculate, and you can calculate that when y lies between 4 to 9, the probability is 11 by 14, and when y is greater than equals to 9, the distribution function is 1. So finally the cumulative distribution function of y is nothing but exactly this 1, and we got the cumulative distribution function of y. From that I can check now whether y is a discrete random variable or whether y is a continuous random variable. Obviously intuition says that y should be a discrete random variable. So let us check if it is a discrete random variable or not. Obviously they not let us check, you need to check that. So you check that y is a discrete random variable, and then find what is the probability mass function of y. Okay, I leave this as an exercise for you to check that this y is a discrete random variable from this cumulative distribution function, and then to find out the probability mass function of y. Okay, let us take another example when the x random variable is not discrete but a continuous one. So x has this probability density function, and again we take the same function that gx equals to x square, so y equals to x square, and we try to find out the probability. Again the same thing go on, that probability that y less than equals to small y for y greater than 0 can be written in this form, and probability y less than equals to small y for negative values of y will be 0, just like before. But now when I try to calculate this probability now we need to calculate from the probability density function of x, because now x is a continuous random variable with probability density function, this one. Okay. So now because of the range here that x lies between -1 to +1, my y will going to lie between 0 to 1. When x lies between 1 to 2, y going to lie from 1 to 4. So based on that, I will break the range of y. I will break the range of y. What we have done here, that y lies between 0 to 1. Less than 0 is already done. So now 0 to 1, then 1 to 4, and greater than equals to 4. So when y lies between 0 to 1, just before minus root y and plus root y lies between -1 to 0 and 0 to 1 respectively. So that means when I try to find out the probability that, so this probability, when I try to find out this probability, I need to take the integration of the density function over the range minus root y to plus root y, and on the range minus root y to plus root y, the density function takes value, the form of the density function is mod x by 2. That's why I write it mod x by 2 here, and finally when we complete the integration, it turns out to be y by 2. Okay, this integration is a simple integration, just complete it. Now when I go for y lies between 1 to 4, I have two cases. One is, first of all, that minus y minus root y lies between -4 to 1, and plus root y lies between 1 to 4, just like before. Okay, so when I have this thing, now you see that the density function in this range is mod x by 2, and density function in this range has some other expression which is x cubed by 3, which is x by 3. Similarly, in this range also x by 3. So definitely now I have to break the integration into both two parts, one of this part, another of these two parts. Okay, I am sorry, basically integration, the density function here is 0. Density function here is 0. So that means when I do the integration over this range, this part will not going to contribute anything. This part will going to contribute integration of this quantity, and this part will going to contribute integration of this quantity. Okay, so now that means that for y lies between 1 to 4, that integration turns out to be -1 to 1 mod xy 2 dx, and then x by 3 will be integrated over the range 1 to root y. Okay, that's what exactly we got here. From -1 to 1, it is integration of this one, and from 1 to root y, it is the integration of this one. Okay, clear? So now we have this thing. And this integration you can do very easily, and you will get that this one will be the probability of this quantity when y lies between these two. Similarly, when y greater than 4, the same approach you can use, and it basically turns out that you need to integrate this over the range -1 to 2, and that becomes it 1, because this is the density function. Okay, and so finally you have the probability, the cumulative distribution function of y, which is 0 for negative y, which is y by 2 for y lies between 0 to 1, 1 by 6 into 2 by y, 2 plus y for y lies between 1 to 4, and 1 for y greater than equals to 4. And once you have the distribution function, again you can check whether it is a continuous or discrete random variable, and you can actually show that this is a continuous random variable, and then you can find out that PDF. Again, I leave this one as one of your exercise. Let us take another example. So if you see previous two examples, the first example was x was discrete. The first example we have x was discrete, and in this case we got that y is also discrete. Okay, in this example x was discrete, and then we got x is also discrete. Similarly, in the next example also x was continuous, and we got that y is also continuous. Natural question comes to the mind: does it always true that if x is continuous, y is continuous, x is discrete, y is discrete? And the next example, what I am going to give you, shows that no, it may not be the case where we start with x is a continuous random variable having this PDF, and we are going to show that y is not a discrete, not a continuous one, y is discrete. And intuitively it makes sense because you see that in this case, I take y is equals to box of x, and box of x basically mean that box of small h basically mean the largest integer not exceeding x. And clearly in this case, we will have that that whatever the value of x, box of x going to take some integer values. So intuitively it makes sense that box of x, which is denoted by y, is a discrete random variable because it is taking some discrete values, not a continuous value. Okay, so let us try to prove this one, try to establish our intuition using mathematics. Okay, so now again we will approach in the same manner that y is less than equals to y. The cumulative distribution of function of y is probability y less than equals to y, which is basically box of y less than equals to y. And clearly it will be 0 if y is negative, because x cannot take value 0, so y also cannot take value 0. Now, when y lies between 0 to 1, again why this backup? This backup based on our intuition, because y can take value 0, 1, 2, 3, 4 and so on and so forth. That's why based on this intuition, we break the range of small y into 0 to 1, then 1 to 2, then 2 to 3 and so on and so forth. For 0 to 1, what the distribution function of y, which is probability box less than equals to y, and that makes that for any value of x which is less than 1, box of y will be less than equals to y for any value between 0 to 1. For example, if you take small y equals to 0.5, that box of x will be less than 0.5 for any value of x which is strictly less than 1. Okay, and this probability now I can easily calculate from this density function, which is the integration of the density function from minus infinity to 1, and which is equals to 1 minus e to the power minus 1. Next, I can go for y lies between 1 to 2, 1 inclusive, 2 exclusive, and this case that box y less than y is basically mean that x is strictly less than 2. And when x is strictly less than 2, this is basically integration from minus infinity 2 of the density function, which is 0 to 2, because on the negative side density function is 0, and which turns out to be 1 minus e to the power minus 2. And in general, if y lies between minus I to I plus 1, you will get this one is the probability. Okay, so we have the distribution function of y is this, and from this one you can easily see that the distribution function is a step function, and from that you can show that y is a discrete random variable, and a discrete random variable, and this is basically one of the example where even though x is continuous, y turns out to be discrete. Okay, so x continuous, later we will basically show that if x is discrete, y has to be discrete. We have no other option. If x is continuous, x can be continuous. If x is continuous, y may be continuous, y may be discrete. That completely based on what g function I am talking about. Okay, I hope that this is clear to you. In the next lecture, we are going to talk about another technique, which is technique 2.